Today, I'll be talking about predictive analytics for Internet of Things enabled systems. Let me start by introducing myself. I'm an assistant professor in the Industrial and Operations Engineering at the University of Michigan. And here are some details about me. This is my website, email, Twitter account, and GitHub code. Okay. So before moving forward, I want to talk about a little bit about our data science lab. From an application perspective, I do focus on real-time predictive and prescriptive analytics. Today, the focus will be on the predictive part specifically. And also another research direction is more theoretical, yet application-driven. Basically, we try to derive methods that improve generalization in deep learning and kernel methods. And most recently, we have been working intensively on federated learning. And I will be talking about federated learning and its impact on Internet of Things towards the end of this lecture. For this talk, I'll stick with a little bit of, I'll talk from an application perspective, and I'll summarize our work that is application-driven in Internet of Things. Specifically, I will start with the research motivation, and then I will talk about predictive analytics for stream data from two different perspectives. The first one is a population perspective, and the second one is a transfer learning perspective. I will end by discussing other research topics within Internet of Things. And these topics will show that IoT cannot be summarized with one set of models, yet most of these models do have indeed some commonalities, which one can leverage. Then I will talk about how Internet of Things is on the verge of a major shift, of a paradigm shift. And it is moving from just Internet of Things to the Internet of Federated Things. And this is where I will end today's talk. Okay. So what is Internet of Things? So how I define Internet of Things is basically a smart and a connected system. So in general, we have a physical component that comprises a system. For example, a smart car, you have the physical components of a car. This is a traditional system. And then you have the sensors that are placed on the car, okay, which allow us to collect data. This is what moves us from a mere traditional system or the physics components to a connected system. And these sensors are often in the form of sensors, wireless networks, data storage, and management techniques. And this was really the key propeller behind IoT. Sensors became very cheap. Data acquisition became more and more easy. And right now we had this unprecedented data availability. However, IoT is based on utilizing this data to do smart data analytics and smart decisions for us to move from a merely connected system to a smart and connected system. So indeed, there is this unprecedented data availability, yet the key is utilizing this data to derive smart decisions and derive a smart system. So what are some examples? We have this OnStar system from General Motors. Actually, this was released around 10 years ago. So basically, General Motors collects some information from cars on the road, and their hope is to keep the drivers informed about the health of their vehicle. For example, if maintenance is needed, then they will ask the driver, it is time for maintenance, perhaps through a text message. We have many smart remote health management systems, for example, asthma management systems. Propeller Health has this device where every time a patient takes an asthma puff, it is recorded, and sometimes, if needed, it's sent to the hospital with all the details regarding the time and the frequency of how many puffs have been used. We have the General Healthcare Insight System, General Electric Healthcare System. They have similarly their Insight System, which collects information from healthcare machines and to monitor their health and make sure that those risky devices are well maintained. And definitely we have smart factories where devices are talking to each other in order to enhance throughput and reduce cycle times. And those smart factories are specifically relevant nowadays with COVID, where most companies are trying to ramp up throughput as much as possible using their smart factories. So what are the key steps in such data analytics? The key steps, first of all, the first step is a descriptive analytics step, where we are trying to answer the question, what happened? For example, if we are monitoring data from a car or from a patient and something went wrong, we want to ask what failed, okay? And we want to try to gain some insight or inference on what caused this failure. So this is the first step, which is descriptive analytics. The next step if we know what component has failed, we can somehow predict how the system will evolve in the future. For example, if we can detect some degradation in the system, we can detect the future degradation or the evolution of the degradation in order to predict maintenance. But the ultimate goal is definitely prescriptive analytics. If I know for a car that failure is imminent within this specific period, then I should do maintenance decisions. I should take an action on maintenance and decide what is the optimal time for me to make maintenance, or what action should I take. However, for this talk, I will be mainly focusing about predictive analytics. So I will specifically focus on how can we combine real data, which comes in online from systems in real time, and historical data for us to somehow try to predict an event that happens in the future. For example, a failure of a specific device. Okay. So with this connectivity that Internet of Things provides, there are indeed many statistical challenges. The first challenge is a direct consequence of the large amount of data that we are collecting, is the high dimensionality of the data. Collecting a lot of large of data from many components of the system, and hence most of our data is highly dimensional. The second thing is definitely heterogeneity. And basically we're collecting data from different components of the system that behave under different circumstances. For example, if we're collecting information from different patients have different external environments that affect their behavior. Then most of our data right now with Internet of Systems, since sensors monitor a system continuously, are of functional nature or time series. They might have some stationary, non-stationary behavior. They often do have autocorrelation. And there are some opportunities. One opportunity is individualization. In the past, for example, in cars, we wanted to find the average lifetime of this model of a car. But right now, since I have information from each specific individual, I have access to all this data. Instead of trying to say the summary statistic on all my population, rather I can say I want to find the remaining life of the car of this specific individual based on his specific data, and so on and so forth. So there is a lot of opportunity to do individualized predictive analytics. And finally, definitely interpretability is a crucial problem in general statistical inference, and specifically in IoT systems. Okay. So indeed, to address these challenges, new predictive analytics methods need to be done, and a lot of research has been ongoing in the past decade along this line. Very interesting research. So today I will try to look from a holistic perspective on what type of research has been done and the philosophies people are taking to address such problems. So the first philosophy I will talk about is a population perspective. Let's take a simple example. We're trying to do predictive analytics from cars on the road. We're collecting data from these cars. These data are in the form of condition monitoring signals. And our eventual goal is to use this data to predict, for example, an event, or to decide on maintenance, or to predict some catastrophic consequence. So this data is often referred to as condition monitoring signals. Why is it condition monitoring signals? Because it's either directly or indirectly reflects the underlying health of a system. For example, if you're monitoring a car battery, you're monitoring its resistance. When the resistance is low, there is a low probability that this car will have a failure soon. But when the resistance of the car battery increases, then the health of the battery is compromised. So indeed, condition monitoring signals are somehow an indicator of the underlying health of that specific system. Okay. So given this condition monitoring signals, CM signals can be seen everywhere. For example, simply, if you look at a light bulb, the brightness of a light bulb is a condition monitoring signal because it reflects its health. And after 80% of the brightness is lost, then this bulb will fail, will not turn on anymore. So in smart home appliances, for example, many recent devices like ACs and HVAC systems are monitoring their energy use. And they monitor how much energy is being used. And this energy use can be classified as a condition monitoring signal because it detects some underlying behavior of the system. Remote patient monitoring devices, I spoke a little bit about the asthma device, but there is a lot of devices right now that monitor pressure, heart pressure, diabetes, even smartwatches right now can monitor many condition monitoring signals that really somehow convey some information about the underlying well-being of a patient. In structural systems, for example, bridges, there are sensors that monitor the degradation, or how much, for example, is the crack length of a specific system. Okay, so let's just stick with one example to just contextualize the statistics here. Let's assume GM's OnStar system. So GM is taking information from cars on the road to its back office or its cloud. And the goal is to do some database analysis and then keep the driver informed about the health. So send back some service alerts to the driver. So basically the data that is available in such a system is we have a historical database from cars on the road, perhaps cars that have lived their lifetime or perhaps cars that are currently on the road. And then we have some cars that we are interested to predict how they will behave in the future, or trying to just understand their behavior in general. Okay, so the general setting from a statistical perspective is as follows. We have a set of n signals, and basically our goal is to use these n-1 condition monitoring signals to predict yn, the last function yn, which is the last condition monitoring signal. For example, these can be resistance curves from 3 cars on the road. And our goal is really to predict the resistance curve for the car of interest. We will assume that yn right now is the car of interest, is the car that we are monitoring in real time. So basically our goal is to borrow some strength from our historical database in order to best predict, be it an interpolation problem or an extrapolation problem, the curve of interest. Okay. So what is the most common perspective of analyzing this problem? It is a population perspective. What is the population perspective? I start with my historical database, which is y1 to yn-1. And then given this my historical database, I build some kind of a population estimate. This population estimate perhaps can be just a parametric curve. I can fit a parametric curve. In this situation, it's just a quadratic line defined by its coefficients, and perhaps some random effects. And then, given this population estimate, as new data is obtained from yn, as we obtain this new data, then we do update this population estimate. And the expectation is, as we get more and more data from that client or from that unit or from that car of interest, our predictions will become more and more accurate. So this can be done often through a frequentist approach, but most people, for example, this is just from an empirical based perspective, you're trying to derive a posterior distribution over your set of weights or your common set of or your common shape function here. So the key idea is we summarize all this information in our historical database into a population estimate. And then given this population estimate, we try to obtain individualized predictions for that unit at hand. Okay, so there are many models along this line. If you look at from a parametric perspective, this is actually a generic set of models that really encompasses a large class of models. For example, our output is some set of regression functions, be it a polynomial, a spline, or a wavelet, and some stochastic process. The stochastic process can be just an independent noise. It can be a Wiener process, a gamma process, an inverse Gaussian process, a Brownian motion, and that all depends on how the system behaves. For example, a gamma process or an inverse Gaussian process have monotonic properties. And if you're monitoring degradation is often a monotonic process. However, they do have independent increments properties, which entails using other stochastic processes, because independent increment properties, which are somehow Markovian properties, are often reflect that the history is not important. But if for example, we're monitoring patients, and patients has a history of some kind of a disease or a mental health issue, then definitely the future will not be only dependent on the current state. So there is a lot of class of models that can be modeled in this sense. Another class of non-parametric models also follows a very similar philosophy. It basically decomposes the population into a set of eigenscores and eigenfunctions. So this is non-parametric in the sense we do not specifically specify this common shape function, but still it follows the same idea. From my entire population, I fit some linear function, which is based here on eigenscores and eigenfunctions. This is commonly referred to as functional principal component analysis, and this behaves as my population estimate. So the basic idea is I start from this either parametric or non-parametric model. I fit my estimates. For example, here I find my coefficients, I find my random effects, here I find my eigenscores. And then as I get more and more data, I can update my population estimate. I'll give you one example here before moving to what neural networks are doing. So let's take one specific simple example. Let's assume we are monitoring a condition monitoring signal, and our goal is to predict the remaining life distribution. So basically, we assume that this is a health signal from a car, and the car fails when this health signal reaches a specific threshold. So let's take this simple animation into consideration. So here, the dashed black line is the true behavior of that specific individual. So we start off by a population estimate, perhaps just a quadratic function, which is in the red line. Then as we get more and more data, we're trying to update our population estimate to get individualized predictions, ones that are very specific to that car in hand or that person in hand. This is a survival probability. Basically, it's the probability that death occurs after that specific time. So this is just a survival curve. This is the estimate for the parameters. Here we're just taking a very simple model, a quadratic function. We're assuming quadratic function with independent noise. So this is the idea that this population perspective is starting from this population estimate. We're summarizing all our information into one estimate, and then doing some empirical base or updating our estimate as we go. And this idea recently also caught on in the machine learning community, specifically in neural networks, through this notion of continual learning, also referred to as incremental learning. The problem is a bit different, as the motivation of the problem is a bit different, but definitely the application is the same. So where they started off with by saying that continual learning is the idea that sometimes new classes are introduced to my model. So how can I update my model without refitting it? Just update my model so that it is able to fit this new class. Another set of motivational problems for continual learning is that if you have a lot of data, you cannot keep your data. Your storage is not sufficient to keep all this data. So you want to throw some data. However, as new data comes in, you want to keep on learning on this new data, yet you do not want to lose predictive power on your old data set. So basically, this is much like this incremental learning, this empirical base, or updating our predictions. So the idea of continual learning, I just give one example of a very famous model proposed in 2017. It's called elastic weight consolidation. This is a frequentist perspective where from their old data, they fit one estimate, W star here. And then the idea is, as you get new data, you try to optimize a loss over this new data. However, you restrict that your new estimate lies within a ball of that previous estimate. So basically, the idea is that I want my fit to still be good on my old data. So I do not want to move or wander very far away from my previous estimate. However, I want to individualize on my new data. So I want to get indeed good estimations from my new data. Okay. So this F often is this Fisher matrix, and this is basically this Laplace approximation of a Gaussian distribution. This is from a more frequentist perspective of solving this similar problem of looking at the problem from a population estimate. Okay, yet this has some challenges. So one challenge is actually you're only using summary information to do inference. So you're not letting data to speak for itself. A lot of the data is being thrown away. However, this comes at the cost of efficiency. When you're just updating a summary statistic, it's much more efficient than just using all your data that you have. Also, many of these models have some parametric assumptions. And parametric specifications are often very sensitive, specifically if we do not know the underlying physics of the system or we have sparse signals. And finally, which is one very important concept that goes against a population perspective, is heterogeneity. So the key idea when we estimate a population perspective, when we estimate a population estimate, we're assuming that somehow the entire population behaves according to this estimate. But that might not be the situation, because different units might have very different behavior. They might actually have different shape functions. And this is an issue in this population perspective. So one simple solution is, for example, cluster your data and fit population perspectives. But then the question, do the data fit in clusters, and how do they fit in clusters? So this is where a different perspective comes into play, which is a transfer learning perspective. So the basic idea of transfer learning perspective is simple. Instead of starting with a population estimate to predict yn, let's provide a shared representation of all our data. So basically, all my functional data is a function of some multivariate stochastic process plus some noise. So this multivariate stochastic process defines the underlying latent functions, which is the true signal. So basically, my goal is to predict f of n. So the key advantage of having shared representation, so you can think about it as just, I'm doing a regression over all my data together. The key advantage is right now I'm able to jump right away from my historical data set to my in-service unit, rather than jumping from my historical data set to a population estimate to my prediction of my in-service unit or my unit of interest. I can directly jump into the in-service unit. So this general setting is, the key idea here is, instead of starting from a population estimate to predict yn, we are rather doing integrative analysis. And this is the key idea of transfer learning. Here specifically, it's under the notion of multitask learning. Basically, the idea of multitask learning is that the integrative analysis of multiple data sets is advantageous compared to analyzing each task. Here, each task is a functional signal alone, or just using a population estimate to update or estimate y of n. Okay. So I try to take I will try to keep this presentation more on the non-mathematical level, but I want to talk about some possible models. These are definitely not the only type of models that are plausible, but this is one class of models. This class of models is basically, we assume this multivariate stochastic process is a multivariate normal distribution. So when we assume this multivariate stochastic process is a multivariate normal distribution with some covariance, this ends up to be just a Gaussian process. So the key idea of modeling this, so we took the easiest distribution and normal and assumed this is a Gaussian process. And the key idea in the Gaussian process is really to model this covariance across functions. So what the covariance across functions is trying to say, it is somehow trying to say how much the functions are alike, and to model the stochastic deviations. So basically, I'm trying to understand what are the commonalities between this function that I'm trying to predict f of n and all the functions that I currently have in the data set. Okay. So this is one class of approaches. This is more a Bayesian perspective on this class. I will talk a little bit at the end to where on a frequentist perspective to solve the same problem. So let's take a look about what are some types of modeling this covariance, okay, in those kernel method type of classes. So one type of approach is a separable covariance. What does a separable covariance mean? This is the covariance between any two condition monitoring signals, okay, is a function of some Tij, some constant, multiplied by a covariance shared across all signals. So basically, the idea is that all outputs share the same covariance function. They only differ by this parameter Tij. So basically, the key idea of separable covariances, which have a long history, they're often discussed under this class of linear model of regularization, is that somehow all your outputs are a rotation of each other, either a rotation or some kind of a scaling and rotation of each other. However, this covariance is restrictive because it somehow forces all outputs to have the same marginal covariance. So let's take a look at this example. We have these two data sets. two functions that, and my goal is to try to predict this function. However, under a separable construction, then what happens here is the second function is forced to have a similar length scale, or just to be a rotation of this function at hand. Okay, and hence the predictions are not very strong. So basically, this approach of modeling or separability in the covariance somehow forces correlation or forces functions to follow similar properties. Okay, so so another approach in these kernel methods is a non-separable covariance construction. And interestingly, this idea was indeed introduced to statistical literature as in 97, but it only became popular in 2010. And more recently, people have been using it more often, is that this same Gaussian process, that the Gaussian process, instead of directly specifying a covariance matrix or defining the covariance in a Gaussian process, a Gaussian process can be constructed of a convolution of some kernel with some latent process, with some latent function, perhaps a Gaussian process. And if this is Gaussian, then since the convolution is a linear operator on a function, then the final process is also a Gaussian process. So why this is important? This construction is important simply because if I can construct a Gaussian process from a latent function, then if I share this latent function across different outputs, then different outputs can be modeled using different kernels. So in this situation, this output will have this specific kernel that defines its behavior or its unique features. This output will have this specific kernel that defines its specific behavior. So basically, this is a generalization of the separable covariance, where each output can possess some unique features, but still has some shared features across all the components because they all share the similar latent functions. So this is one of the approaches, and this goes back to our simple predictive example. If we take this perspective on enabling these shared latent functions, then what we allow is that different functions do have some unique features, but also they do share some commonalities, and hence our predictions become much better. So this is a class of solving this problem through this multivariate stochastic process, just assuming it's normal, and solving it using kernel methods, where the goal is somehow to promote heterogeneity and allow different clients and allow different users, different condition monitoring signals to have their own unique properties. And at the same time, a Gaussian process is a non-parametric process. So a key advantage of such approach is that we are somehow not placing any strong parametric assumptions on the model. There are some assumptions, but still from a Bayesian perspective, a Gaussian process belongs to the class of non-parametric Bayesian models. Okay, so let me just give you an example here on our modeling approach. Suppose we have this f1 to fn minus 1, which are the latent functions in my historical database, and my goal is to learn fn. Then I can convolve latent functions and share them. And basically what happens is xn encodes information that are unique to this function that I'm trying to predict. And x1 to xn encodes xn minus 1, this should be here, encodes information that are shared with the functions in my historical database. Okay. So this idea of, okay, I grouped all my data, I made this big model, I have this big loss function, and I tried to implement it using multitask learning. So let's take an example here and see how it behaves. So here in my historical database, I have two signals, and each one has a very different parametric form. And it behaves differently. And without putting any parametric assumptions on my model, can I somehow capture the unique features of each? So here is an in-service unit belonging to the first function and an in-service unit belonging to the second function. As you can see, as we get more and more data, the model is automatically able to infer to which function you belong and do the predictions accordingly. Okay. So this is, and definitely as you get more and more data, and this goes back to this empirical based approach, you should become more confident about your estimator and your predictions become more and more accurate. So another approach is a frequentist perspective. I will not talk a lot about this frequentist perspective, but this frequentist perspective on multitask learning is we define a loss function. Our loss function in the Gaussian process was basically a loss function, was basically the multivariate Gaussian likelihood, just the distribution, the density. And here, this is a loss function. We are assuming some linear relationship. And then multitask learning is done through this regularization. Basically, R is some regularization, and omega is a set that defines the structure or the relationships across tasks. So these relationships are either learned or these relationships can be pre-specified. So this, just by minimizing this problem, this is frequentist perspective, one can somehow get weights that share information across each other, that share information and borrow strength from their functions. Here, this is a linear construction. This is a very common construction of multitask learning. Okay. So I want to give you some models about this idea of transfer learning, where we pull all our data together and we somehow build a shared representation of all our functions to be able to do the prediction. Okay. So one thing that one needs to notice in this transfer learning is the idea of negative transfer. What is the notion of negative transfer? In many situations, if functions are not alike, then their integrative analysis will not bring any benefit. Rather, it will hurt the system. So in this situation, you can see I took two functions, I modeled them separately. Here I use the Gaussian process. One can just use some spline or some parametric formulation. And here I did this integrative analysis. If correlation is forced and the functions are not that flexible, then what will happen is somehow this function will say, okay, the second function that I want to borrow strength from is very smooth, then it will give me very smooth predictions. So in many situations in transfer learning, when you force correlation or you force functions to borrow strength, you can lose prediction accuracy. Okay. So this is what is referred to as negative transfer. So here I want to talk a little, I want to just present one modeling approach that we have recently, that we worked on, that somehow tackles this problem, that combines a frequentist and Bayesian perspective on tackling this problem. And basically, if we have these two functions, and we know they share a latent function, in the convolution construction, each two functions share some latent function, and they have their own individual latent functions. And then if we put a penalty, if we regularize this latent function, much like what this frequentist approach to multitask learning is doing, we put a penalty on multitask learning, on this shared latent function. Basically, what we are saying, then what happens is, if these two functions should not be predicted together, then their predictions will be independent. Actually, we indeed have showed that this approach of regularization of the latent function possesses what we call an oracle property. The oracle property is that if these two functions should not be predicted together, then asymptotically, this latent function will be penalized to zero, and each function will be predicted independently, much like we are modeling them using independent Gaussian processes. Okay. So this goes to saying that from a transfer learning perspective, one should be very careful about this notion of negative transfer. In the population estimate, this notion is a bit reduced, because in a population estimate, basically the rare cases will be hidden, will be lost. So your population estimate will perform very well on the majority cases, which somehow suit your entire population. But on your rare cases, it will have very bad performance. Okay. So here I want to talk some other research within this notion of IoT that we have also been working on. And you can see the commonalities across this work. So the first work is the multi-stream sensor data, and this work is by Salk. So multi-stream sensor data, here it is important to note that what we have been discussing is basically we're trying to borrow strength across functions. But in many situations, from each car, we are not just collecting one signal. From each patient, we're not just collecting a cholesterol has signal. We might be collecting many signals. For example, from a car, we might be collecting the temperature, the voltage, a degradation signal, so on and so forth. So the question is how to extend such results to a multi-stream data setting. And this similar problem can be seen in smart home appliances with basically monitoring multiple different components that have different signals that one can monitor. Similarly, for wearable patients, one can be monitoring the heart rate, the sugar level, and so on and so forth. And in this situation, the goal is really to not only borrow strength across these functions to predict the in-service unit, but rather borrow strength across all signals. Okay, this is one of the problems. I do not want to talk about the solution, but I just want to discuss some of the problems that are often encountered in Internet of Things enabled systems. And they do have some solutions. For example, in this situation, we combine this FPCA idea for non-parametric estimation and the Gaussian process somehow to be able to predict and borrow strength across all the signals for the in-service unit. And this was tested on a real-life data set from NASA, where they have their jet engine propellers, and they're collecting information from multiple signals on their jet engine. So another problem which is common in this IoT system is joint modeling. So in many, right now I was discussing about time series data. In many situations, you also have survival data. So you do not only have time series data. For example, for cars on the road, I might have the resistance signals, but I also can have some failure data, which is the time to event data. From patients, I can also have some continuous signals, but I can also have failure events or the time when critical events happen. And joint modeling is an approach where somehow I try to utilize my time series data to predict the probability of a critical event happening. And so this is, for example, this is a simple illustration of joint models, which are often relevant in IoT settings. You have some continuous signals, and then you have your failure event. For example, this is a patient, and then this patient, this first observation, let me try to highlight. Oh, okay, never mind. So in this situation, this is a specific patient here, and then this patient has this failure event at this specific time point. And similarly, we have another patient, and this patient has a similar event at this time point. And the goal, as we collect more and more data from new patients, can we predict the probability of a survival event? This is what we call joint models. And so joint models, there are many joint models, but this is one modeling way that we have. This is the hazard function. This is the well-known Cox proportional hazards function. And then the covariance can be modeled as this convolution process or the Gaussian process that I have just showed you. Just this goes saying that event data is indeed of importance in condition monitoring signals, and joint models have recently gained a lot of attention towards solving such problems. Another interesting issue that rises in Internet of Things enabled systems is what we call weak supervision. So we have these multiple functions, but in many situations we might not have labels from those functions, or the labels are missing. Let me give you an example in a specific setting, in a healthcare setting. So let's assume you have two groups, perhaps male or female, and these curves are the curves that monitor your insulin uptake versus the C-peptide level, for example. Okay, so in many situations, you will not have the labels whether this person belongs to group 1 or group 2. For example, people will prefer not to specify their ethnicity, their gender, so on and so forth. But the question is, should I throw away this data? The easiest approach is, okay, let me fit a transfer learning approach using just the available red dots or the available blue curves. But a better approach will be indeed to utilize these unobserved tables. And here we developed this approach called weakly supervised multi-output regression. And this approach, so let me just note what weakly supervised means. So here, because you are missing labels, it is often called unsupervised learning or semi-supervised, because some labels are available, some labels are not. So this is a semi-supervised system, but weakly supervised here indicates that in many situations, you might have some prior knowledge, whether this person belongs to this group or not. So in a weakly supervised setting, this prior knowledge can be augmented to recover the curve. So let's take a look at this small example. Just from those small set of data, we are able to recover the underlying true curves. And similarly, in an imbalanced situation, still our approach is able to recover these imbalanced curves. These are just one example. Another example in an IoT system can be when qualitative features are included. For example, at one point I was working with General Motors, and we realized that their batteries, we're trying to predict the condition monitoring systems of their batteries. And we realized that they have 2 generations of batteries, and their batteries somehow have different performance. These 2 generations do have commonalities, but their performance is indeed different. And under this kernel method perspective, where we are modeling this covariance, then somehow we need to provide a distance measure across these qualitative features. We want to say that, okay, batteries, condition monitoring signals from similar batteries might have more commonalities than condition monitoring signals from batteries that come from different generations. This is much like the idea of this weakly supervised setting. We have some data which might be different or unobservable, but we want to leverage this data. We want to leverage this additional information. And basically, we somehow create some distance measure across qualitative features. Most recently in this Internet of Things, I've been working on what we call here battery storage decisions. And this is a very interesting problem, because this is, I'm not sure if you are familiar with the duck curve, but the current statistics, this is what we call the duck curve in California. So current statistics indeed show that on a yearly basis, more than 30% of the electricity load in California is met by either solar or wind energy. Okay. However, for certain days, this renewable energy, solar and wind energy, can contribute up to 50% of the demand. Okay, in the daytime, but in the evening, it can go as low as 20%. And this is understandable because in the evening, there is not much solar power anymore. Okay. So the problem they faced in California is what they call the duck curve. Okay. So around 2 p.m., solar plants produce a very, very large amount of data. Okay. So this duck curve is the net load. So basically the net load is the difference between the demand and the solar and wind farm. Okay. So around 2 p.m. there is a lot of sun, and hence the net load is very small because I can do the production. But then as the sun goes away and most people go back home from their work, then somehow the demand increases rapidly. And what happens is that the solar energy cannot meet this demand. And this ramp up area at 6 p.m. in California has been costing them a lot of money. Because in general, these conventional power plants, like fuel-based power plants, need some ramp up time. So they need to stay on for the entire day to be able to give energy at the specific, to be able to ramp up fast and give energy at that specific time of the day. So this is the well-known this duck curve problem in California, and we try to solve it using a battery. The key idea is simple. Can we store some data, some energy, so that we can utilize it around 4 to 5 p.m.? And where IoT comes in is we have information about the demand, and this information is updated with time. So if we can predict the future demand and the supply, then we can do some battery decisions. We can look and see, okay, how much should we store in the battery for the future? Okay, and these are some results from our battery storage decisions. So if you think about it in this way, if you are not predicting the future or using these sensors to try to see how much demand is in the future, your decisions are simple. Your decisions are, if your demand is more than your supply, just store, and vice versa, then just purchase energy. However, if you can predict the future supply of energy, perhaps at some times of the day when the energy is very cheap, you say, okay, let me let me charge the battery at this specific time, and then let me buy the energy that I need to meet the supply. And then in the later times of the day, at 6 p.m., where the energy is very expensive, then I can discharge from the battery. So these are some situations where Internet of Things are indeed of very important and predictive analytics in this sense. Okay. So I will end today's talk by talking about the Internet of Federated Things. So I want to note that IoT, as we know right now, is on the verge of a big change. And basically, this change is in the form of federated systems. So this is why I call it the Internet of Federated Things. And currently at the University of Michigan, we have a joint effort from multiple faculty to write a paper. It's basically a survey and then a vision paper of the future of Internet of Things. Okay. So the current IoT system that I presented is a system where we have devices or clients. These devices upload their data to a cloud or a data center, and all the data analytics is basically done on the data center. Okay. So this is what we call centralized model training. We have gigantic amounts of data uploaded to the cloud, and then there is these big models learned on the cloud, and these models are then deployed to the cars on the road. However, the future is a bit different. The future is rather a federated future. And so let me just give an example and explain the key idea. So right now, instead of devices or clients uploading data to the cloud, the question is, can we learn a model without the need for clients to upload their data on the cloud? For example, if I'm trying to learn this big deep learning model in the cloud, do I need my clients to upload their data, or can I use some computational power on the clients to learn this big model? So for example, instead of this client uploading their entire data set, can they do some small computation and give me a gradient? And then using this gradient, I can just learn this big model on the cloud. This is where federated systems, this is the key notion behind federated systems. It's basically moving away from the cloud to the crowd, where inference is not done on the cloud. Rather, devices just send focused updates to a central server, and this central server only aggregates these updates to build a big model. Okay. So what are the key advantages here? The main advantage is privacy. Because by bringing training to the device, the users no longer need to share their valuable information. Instead, their data is kept local. And this is possible right now because all your devices, think about your phones, your smartphones. So take, for example, these smartphones. Currently, not currently, previously, when Google wants to learn, for example, a next word prediction model for your phones, when you are trying to write on your perhaps WhatsApp, they're trying to predict the next word. Okay. So what happens here is, how do they learn this model? They upload data from phones, and then based on all these uploaded data, they learn this big model, this next word prediction model. However, in these federated systems, your phone does not provide data, but rather your phone runs a small algorithm. Right now, most iPhones have the capability to estimate gradients. They have the capability actually to estimate networks themselves. And then they just upload a gradient, or they just upload the minimum information needed to learn this model. Even for cars, this is right now possible, because most cars right now are being, with the evolution of electric cars, most cars right now have these the so-called AI chips, where they can run some computations on the edge. Okay, so right now one key advantage is that user information is kept local, and this addresses a huge concern of privacy. Another concern, which is very important, is computation. So as we have more and more IoT devices, right now we have more than 1 billion devices and IoT devices connected to some kind of a cloud. There is no data center that is able to handle all this data and fit such huge models. Indeed, most of cloud data centers, they somehow subsample from your data or take the most relevant data, or they just do more controlled trials to fit these big models. However, right now, with this ability to use the compute power on the edge, massive parallelization is possible. Because basically companies right now are using the computational power of your device, of your phone, of your car. They're not just doing all their computations on their cloud. And this is where computational and storage needs are reduced. Actually, also cost is reduced for such companies, because this idea of federated learning embodies the principle of data minimization. I only send the minimum amount of data that is needed to learn the model. And this also comes with some energy savings, because right now your data uploads are really restricted to the minimum information needed, or focus updates. And another important advantage of such IoT-enabled systems that are federated is diversity and fairness. So think about hospitals. In the US, 2 hospitals cannot share information and cannot learn a joint model together. However, right now with federated learning, 2 hospitals can learn a joint model, can borrow strength from their data without the need to share their information. Okay, and similarly with IoT, we can get data from geographically dispersed locations. This promotes fairness and diversity in our estimators. So these are key advantages of this future IoT system, which is defined by moving the training from the cloud to the edge device. Okay. So some of the challenges in this setting currently, as we know, this Internet of Federated Things is based on building this big model, on the aggregator, which is a global model. So somehow we are saying that there is one model that fits all the clients. But this might not be the optimal situation. In many cases, we might want to fit a personalized model. So the question, how can we personalize in a federated setting? How can we take this global model and somehow fine-tune it to each individual client? And is this a possible task if you have all these clients that actually, they're not giving you their data. They're just giving you summary statistics. But one key idea is use the same idea of this population estimate. So this here becomes your population estimate. This here becomes your population estimate, the aggregator. And then from your new client, you try to update your population estimate. Okay. Also, you can think about it from a transfer learning perspective. Forget about the aggregator. Can I form a shared representation over all my clients and learn a model without data sharing? And all these questions are around personalization and individualization. And it's very interesting to investigate whether a population perspective or a transfer learning perspective can achieve optimal personalization in a federated setting. Another very interesting topic that came out around 4 years ago is somehow in between learning a global model and learning a personalized model. It is what we call meta-learning. So the key idea behind meta-learning is rather than learning a model that does good predictions on all clients, we try to learn an initialization. Okay, we try to learn a set. For example, in a neural network, we try to learn a set of weights W. So as if I give W to a specific client, and this client does some small training on their own data, then basically they can get very good personalized models with just minor training. Sometimes in stochastic gradient descent, let me just show you the specific model, for example. When we're learning a network, the loss function is basically the loss function over all your data. And this loss function can be the squared loss. Okay. But in a meta-learning setting, our loss function, what we are trying to say is I want to find the set of weights that gives me the best loss when I do one step of gradient descent, or perhaps stochastic gradient descent. So the key intuition here is what? Is I want to give the clients a set of weights W that are not optimal for all clients. No, they're not the best global model, but rather they're a set of weights where if the clients takes these weights and does a small update, which goes back to our idea of a population estimate and updating the population estimate. If I give W, which is this population estimate, and the client updates this population estimate, then with very minor steps or very minor computations, they are able to reach very good personalized states. Okay, this is the key idea of starting from a population estimate. Basically, we are building the best population estimate for personalization in meta-learning. So these are three very interesting questions in federated learning. And remember, the key idea here, we do not have access. The central server, the cloud, does not have access to data. It just has access to summary statistics. So many interesting questions raise: what clients to sample? How to do the samples? Is there bias? How to ensure fairness across different clients? Will a global model work? Will a global model fit all, or do I need personalization? Is it viable to personalize when I have all these millions of clients right now, specifically with federation? I can have access to millions of clients. Is it possible to do this multitask learning and personalize? Or is it better to do meta learning? Just train an initialization and let clients initialize themselves. These are all interesting questions to be answered in this future of IoT systems. So let me just end by this slide that IoT is a combination of multiple systems: smart health, smart manufacturing, smart energy, smart Tele-Service systems, which I've been talking about in GM. Really, the goal eventually is to build the smart city, which is a combination of these different aspects of IoT. This is my talk. I hope I've given you a general overview of predictive analytics and some class of models. This is by no means an exhaustive list on all the possible models that can be used within IoT, but this is a glimpse on some of the problems that often arise in such systems and how they can be solved. Okay, thank you everyone, and I'll stop for questions.
Yeah.